Good to see you all here. My name is Ede Meijer, I was just introduced. And I'm the founder of PyGrunn. It's a startup that's focused on helping businesses improve their purchasing process by using deep learning. So I'm helping them optimize their stock and reduce their costs. And yeah, as mentioned, I used a Java deep learning solution, but ran into some issues and started looking for alternatives, which I found in TensorFlow. I was pretty surprised by the elegance of some things in TensorFlow, and I wanted to show you how it works and have a nice demo for you. But before we dive into deep learning, I want to tell a bit about machine learning in general. So machine learning, learning from data without being explicitly programmed. What I mean by that is that if you have a lot of data and you want to create a model that can be used for making predictions on that data or similar data, then instead of trying to create your own model by hand, you can use the power of machine learning to automate this process. So how that basically works is you have a lot of examples, a lot of data, and you feed this into a machine learning model along with the desired outputs for every example you have. And then this machine learning algorithm will automatically tune itself to produce, well, as close as possible to the desired outputs as you want. Of course, how good it is in doing that depends on the kind of model you use. And I want to quickly introduce a few techniques that are generally used. So first is linear regression. Linear regression basically tries to fit a straight line through a set of data points. In this case, we're trying to predict the degree of crazy given the degree of hot, and apparently there's a pretty strong correlation here. So how that works is, well, the little formula describes this very nicely, y equals a plus b times x. And here, x is the given value, it's the value of hot, and y is the value we're trying to predict, the degree of crazy. So a and b are also called intercept and slope in this case. The intercept is the point where our line crosses the y-axis. As you can see, it's not exactly at 0, it's some higher value. The b is the slope. It's the degree of the amount that the line goes up or down given increasing values of x. In this case, it's also slightly positive value as it goes up for every x. So that's one kind of model you can use to make predictions. For new values of hot, it will still give a reasonable prediction for y. Another type of machine learning algorithm is, well, it's like a little brother of linear regression. It's logistic regression. It's used for classification rather than trying to predict continuous values. In this case, we have orange dots and green dots. This is very similar to the talk we just saw from Zacharias. Maybe you were there. And he was trying to classify cats and dogs. Well, it's very similar in that we have a slope and an intercept, although it's actually in a different dimension. But whatever. This is a similar kind of technique for classification. Something entirely different are decision trees. This is also a classification technique, although it can also be used for regression, but instead of applying a linear formula, it takes yes-no decisions and trying to split the data set for certain variables. Here we're trying to classify what people think of the weather, and if it's raining, the weather is bad. If the temperature is below -10, it's bad. But then if it's snowing, it's good. And if it's not snowing, it's only good if the temperature is high enough, above 15 degrees. And these kinds of models can be trained by taking all the examples and outcomes and trying to split it as good as we can between bad and good on one variable at a time. This is how these trees are built with machine learning automatically. So this is not a manual process. Well, and finally, of course, there's neural networks, which is what this is all about. Neural networks are layers of nodes that are connected between each other. Every node from every layer is connected to every other node in the next layer, as you can see with these lines. And every connection between every node has a particular weight, which can be positive or negative. So in the input layer, we just input our x value, just like with the linear regression. These are all numbers. They're being multiplied by these weights, go into the hidden layer. They're being summed up, and then a nonlinear function is being applied. And this is what actually gives neural networks their capacity for learning complex relationships between the inputs without any nonlinearity, which means like, I'll get get to non-linearity later. But by applying that, it can learn relationships. And then it goes to the output layers being summed up again. And this is the Y value that comes out of the output layer. Now, our machine learning algorithm will compare the desired outputs with the actual output values from the neural network and try to tune all these weights from all these connections until all the outputs match as closely as possible with the desired output. So this is an ordinary neural network, but we're here to talk about deep learning. And deep learning is also about neural networks, but this time not with just one hidden layer, but with many hidden layers, like this. And the general idea is that every layer in a deep neural network is able to extract features on an increasing level of complexity or a higher level of abstraction. So a nice way to demonstrate this or to visualize this is by looking at the intermediary steps in a so-called convolutional neural network. And this is a type of network that deals with image data. And here's an example of a neural network that tries to classify or recognize facial images. So as you can see in the first layer, the only thing it really extracts are like shapes, simple shapes, primitives like squiggly lines and dots and circles. But in the next layer, these features are being composed again and are turned into higher level features like eyes, parts of noses, mouths, etc. And these features, again, are being fed into the next layer, which is able to put it together to construct entire faces or recognize entire faces. So every layer learns one level of abstraction until the desired output is reconstructed or recognized or whatever the goal of the neural network is. But this is the underlying idea of working with deeper networks than just one hidden layer. So let's look at a few use cases, because facial recognition is by far not the only thing you can do with deep neural networks. Other use cases include speech recognition, image recognition, like we just saw, image captioning, where the neural network is supposed to describe with text what's going on in an image, natural language processing, like translation or sentiment analysis, and recommendation systems, for example, on a web shop where you're trying to recommend the products to a customer that the customer is most likely to buy, for example. Can also be applied or done with neural networks. And finally, text generation. This is actually something I'm going to show you how to do with TensorFlow, because I'll show you why. Before we do that, however, I want to quickly show you how this training process actually works, because we just start out with these random weights, and somehow the machine is supposed to tune them until the output matches the desired output. And how does that work? Well, this is a process called gradient descent. It applies to neural networks, but it also applies to our simple linear regression case with our hot and crazy model. And I'm going to show you with that example how it actually works. So here comes a little animation. And what you see here is how the model iteratively learns how to tune the line to closely match the dots. And on the right, we have the same graph we saw before with hot and crazy, but on the left, we have the intercept, so that's where the line crosses the y-axis, and the slope plotted on a chart. And you can see that depending on the intercept and slope values, the total error, which is the total distances of all the dots to the predictive line, is really dependent on the slope and the intercept, and there's one global optimum. So we start out with the really wrong line, and you can see that it has a pretty high error. But you can also see that it doesn't go straight down in a straight line to the global optimum. And that's because of the way gradient descent works. You have to imagine you are a blind guy standing somewhere on this landscape of error, and the only thing you can feel is the slope of the ground under your feet, and you're trying to find the optimum. So the only thing you can do is go down the steepest path you can find. And if you look at this image, you can see that it's not straight to the optimum. First, the intercept goes up, and then the intercept goes down. If I show this again, you can see that the intersection with the y-axis first goes up, and then it goes down again as it finds the local optimum, or in this case, the global optimum. So this is pretty much how gradient descent works. It finds the gradient, which is the slope, and just follows it all the way down to the optimum. This is important to know as we're going to implement this in TensorFlow in just a minute. So now, time for TensorFlow. What is TensorFlow? According to Google, it's an open source software library for machine intelligence. And they're doing pretty well. They have a lot of traction, a lot of users, and a lot of frameworks being built on top of them. But today I only want to focus on TensorFlow and not on the frameworks being built on top of them. So TensorFlow, what are tensors? Tensors are arrays. Everyone here probably knows arrays if you're a Python programmer or any programmer at all. So a zero-dimensional tensor is just an ordinary number. 1D tensor is what we programmers know as arrays, but in machine learning it's usually called a vector. It's just one row of numbers. 2D tensor is usually called a matrix. It's like a 2D grid of numbers, etc. So 3D is, well, just called a tensor. It's like a cube of values. This goes up into as many dimensions as you want. So how do they flow in TensorFlow? Well, TensorFlow is built on the idea of computational graphs. And every node in the graph is a computation, or they're called an operation in TensorFlow. And between these operations, the tensors, or our data, our values, they flow from one operation to the next. So here's our formula again for linear regression, y equals a plus b times x. And assuming that a, b, and x are just constant values, in our case, zero-dimensional vectors, so they're just numbers. First, we have to multiply b with x, so there's a node that does the multiplication, and the tensors flow into that node. And then the result of that, the output of that, together with the constant value of a, is being fed into the inputs of the addition node. And the result of that is just given a name y. It can be reused later to build or to add into other inputs of other nodes into the graph. So all computations in TensorFlow, they're like a big graph. But if you think about it, any mathematical formula you ever encounter can be seen as a graph. It's just very explicit in TensorFlow. And if you do this in TensorFlow, you don't have a result. You only have a structure that you can execute. And only if you execute it, if you run it, you will actually get your output value. Now time for some code, because that's what we're here for. Linear regression. So I just showed you how this backpropagation thing worked, fitting a line to a series of dots. So we start by importing the TensorFlow library, and we call it TF. And then we need two trainable variables. These are the intercept and the slope that we are going to optimize to fit our line as good as possible. In TensorFlow, we define them with variables. Variables can be optimized by the gradient descent optimizer. We start out with arbitrary but wrong numbers, intercept of 2, a slope of -1, and that's not what we want to achieve. So we define some dummy data. Our x, that's our given data, will be the sequence 0, 1, 2, and 3. It's just a constant value. And we want to model an intercept of 1 and a slope of 0.5. So if you apply the y is a plus b times x formula to that 0, 1, 2, and 3, you get 1, 1.5, 2, and 2.5. And that's what we're assigning to the y variable here. Remember, we're still dealing with nodes, so there's no actual calculations being done so far. The next node we're defining is the prediction the model will make. Here's our formula again, x times slope plus intercept. This defines the line based on intercept and slope. Again, this is just a node in the graph. Now we're going to run it. In TensorFlow, you need a session to run graphs. So we create a session and we do some ceremony about initializing global variables. This is necessary to make things work. Not very important. Next line, however, is we're printing the result of running the prediction node. And as expected, we get 4 numbers. They're 2, 1, 0, and -1, which correspond to the wrong intercept and slope we're starting out with. So 0, 1, 2, and 3 combined with that intercept and slope gives you this downward facing line that starts at y is 2. So that's not what we want. We want to optimize this. In order to optimize things, we need to know what the error is. So remember the error surface I just plotted? We're defining the formula to determine what the error is right here. And it's just the difference between y, our desired value, and the prediction the model makes. That's y minus prediction. However, we are squaring it. It has 2 advantages. One is we always get a positive number, so we can always try to decrease the number. The other one is we get a nice, smooth, circular error surface instead of more like a triangular or pyramid shape, which is harder to optimize. It actually has its use cases, but we're doing a square here. Now we do have squared error. It's being printed down there, sys.run squared error, and on the right you can see you get 4 values, but we're trying to minimize 1 value, of course. So we're taking the mean of these errors. That's what you do with tf.reduce mean on the squared error. It's the mean squared error, that's what MSE stands for. We're also outputting that, and it happens to be 4.375. Well, that's pretty big for just 4 numbers. Now we're going to fix those intercept and slope variables. We're defining one more operation, calling it train up. We're creating a gradient descent optimizer. That's the blind guy walking down the error landscape. We're giving it a learning rate, which is basically the step size it takes. It shouldn't be too big because then it just takes big jumps and might jump right over the global optimum. If it's too small, it takes forever to get there, so you have to tweak that a bit. That's actually one of the most important parameters to tune when doing deep learning. We ask it to minimize the mean squared error. This is where the magic actually happens in TensorFlow, because TensorFlow fully automatically determines this slope, this gradient, throughout your entire computation graph, and that is pretty cool because usually you're dependent on people pre-calculating these kinds of things for you, writing optimizers that, well, can only work with fixed kinds of layers, for example, but it's all out of the box in TensorFlow, so that's really cool. This gives us a training operation. Again, it's an operation, it's a node in our graph. So now we need to optimize things, but we can't do it in one step. We're going to take 100 steps, 100 small steps down this error surface. So we're iterating over a range from 0 to 100. And we're running a few operations in one go, every step. The training operation, and we evaluate the intercept and the slope, because we want to check during training what they are converging towards, and the mean squared error to check if the error is actually going down. We run it all at once, and we get all the values back. We're assigning them to nothing, A, B, and R. And every 10 iterations, we just print our values. So on the right is the outputs, and you can see in the first column is the iteration count from 0 to 90, because, you know, modulo 10, 100, you never get there, but because it stops at 99. And you can see that the intercept and the slope are actually converging to 1 and 0.5, which are exactly the values we used to create x and y. Also, you can see that the error is going down. So this is gradient descent in action implemented in TensorFlow, optimizing some linear regression problem. So it's really cool, but it's not deep learning, but at least you know how TensorFlow works now. So now we want to do deep learning. And I've been thinking a lot about what are we going to do? What I'm going to show these people? And I was looking at the site, and I saw this robot with this Trump doll, and I was like, oh, maybe we can make it talk. But again, we're doing deep learning, so we need a lot of examples. And where do you get a lot of examples of Donald Trump talking? Well, yeah. This guy produced 30,000 tweets since 2009. And I filtered out stuff like retweets and mentions and that kind of stuff. But we still have 20,000 usable tweets. So that should be enough for a nice toy example, right? OK. So let's talk about the model we're going to implement. I have to be quick because there's not much time left. We're going to do character modeling with a recurrent neural network. A recurrent neural network acts on multiple time steps, one after another, for every example. So one example is a series of characters. There was the letters in the tweets and spaces and the exclamation points and everything. And we're feeding them into the network one by one. And for every character in every tweet, we're trying to classify what the next letter is going to be. So this is where the LSTM layer comes in. It's called the long short-term memory layer. And this is a kind of node or cell in the network that can keep state by feeding its internal state back into itself for every time step. So in this way, he can build context with which he can remember the current word or the sentence he's in at that moment in time. And remember, if you're looking at this graph on the left, these are the layers, but they're actually, every layer has all these nodes, and all these nodes are connected with one another. You're just seeing single arrows here, but it's like the graph I showed you before. There's lots of nodes going on here. So that's the LSTM layer. It will keep context for the sentence it's generating. Then we add two rectified linear unit layers. They add this nonlinearity that, like I said, is very important to actually being able to model complex behavior or complex relationships. We just used two of them because, well, we're doing deep learning, so has to be deep. And finally, we need to give a probability to every character. What the probability is that that character will be the next one in the sequence. But if you think about the output of a ReLU layer, and we're multiplying every output with all these weights, and we're summing them up again, then we don't have a nice probability distribution. There might be negative values and big positive values. So softmax just takes these values, applies some magic, and makes sure that the output is a probability distribution that sums to exactly 100%. So we can take characters that are most likely to occur next when we're sampling, when we're generating a new tweet. One thing I want to show you, because I'm not going to show you how we're collecting all these tweets, how we're cleaning it up, and how we're creating the data set, but this is pretty much how the data actually looks like. If we have one example that says hashtag Trump 2016 and wanted to predict, well, the next letter, of course we can't predict with the first actual character, which is the hashtag, because we wanted to predict the hashtag. So we introduce one artificial extra character, which is like the start of tweet character. Here I used an arrow sign to indicate it. But we're converting every character to an integer value that represents the index of the character and all the unique characters that exist in all his tweets. And the special character just gets number of characters as integer value. It's zero-based, so it's just one extra character. And for the labels, as you can see, it's the same numbers, but shifted left by one position, because that's how we get the next character. Here also we have a special character. It indicates the end of the tweet. We also want our model to predict when the tweet is done, otherwise it would just blather on forever. And finally, because every tweet doesn't have the same length, but our input data comes in 2D chunks, like every row is an example and every column is a position in the sequence of characters, we need to zero pad it on the right, but our error function does need to know which values are not relevant, so we can adjust for that. That's what the mask does. If there's 2 extra time steps we're not using, just put zeros in there. Okay, it's time for some code. It's going to be a lot, so I'll try to make it quick. Dataset.py. Here we load in a bunch of NumPy arrays, the features, the labels, and the mask, as I just showed you. They're all 2D matrices with number of examples by maximum number of time steps. And we're just assigning it to one object. But we also, I built in a function to split it into a training set and a test set, so we can, during training, evaluate how well it is doing on examples it has never seen before. I'm using a ratio of 10%, which is a bit low, but we don't have that much data, so I want to use as much as possible for training. Now this is the model. This is where we actually define the TensorFlow graph. So let's just start here. Our model has a lot of parameters. First one is the list of characters. These are just all those characters, and we need that to be able to reproduce actual characters based on these integer indices. We also need the maximum number of steps, the width of the first layer, the amount of nodes in this first LSTM or recurrent layer, the amount of nodes in the second layer, the amount of nodes in the third layer. Actually, they're called L1 and L2 here, but you know what I mean. And finally, the learning rate. This is this step size that the blind guy is walking down. And one more thing, a regularization constant. And not going to explain it, but it was required to make my model actually converge. So it's just to make sure it doesn't explode during training. Now, just like with the linear regression, oh no, it didn't do that actually, sorry. We're creating 3 placeholders in TensorFlow, and placeholders are, well, actually the name conveys it pretty well. They're just something we can put in data later during training, but at least we need some kind of node to put it into. And yeah, let's go quickly. We have these features. They're integer numbers, but our network cannot really learn with integer numbers. It needs a one-hot representation, which means that instead of one number, if we have like 80 unique characters that are possible, we actually get 80 inputs, all of which are 0, except for the one represented by the integer number. That one is going to be 1.0. So that's one hot. So instead of a 2D matrix, we now get a 3D matrix of number of examples, number of time steps, and every time step has these 80 values that are all 0 except for 1. This is needed to feed into our first layer, our LSTM layer. We're creating a dynamic RNN node, and we're using an LSTM cell. Like I explained, it's a cell that can keep its own state. the number of units is like given in the model, and the inputs are these one-hot encoded features, so we give it this 3D input. It also returns the 3D output, similarly to the input, but with the LSTM units number of, well, the width instead of 80, it gets like, what was it? 250. But we need to flatten it, and this reshape operation here will transform it into a 2D matrix of, well, every row is just one time step, all these outputs for one time step, and we're concatenating all these time steps of all these examples under each other. We can reconstruct it later. I really have to hurry here. So the rest of this logic, it's about doing all these weight multiplications, feeding the outputs of one layer into the next one, and then here with the ReLU applying the nonlinearity. We do it again here, and then we get to the output layer, which applies the softmax function right here, or actually it calculates the loss based on the softmax function. So it compares the desired label with the actual output of a softmax operation, and with this backpropagation, which is defined after here. This is the optimizer, the Adam optimizer down here. It's like the blind guy walking down this landscape again, but this time we're using a different guy because we're dealing with a billion-dimensional landscape here, and this one's a bit better suited to optimize that. Okay, let's quickly continue. Tweet sampler, I'm not going to go through it line by line because of time, but basically what it does is it starts with this start of tweet character, feeds it into the model, gets this distribution of probabilities for every next character. It takes one at random, but still the ones with higher probabilities are more likely to be picked. And then this character is appended to the list of characters so far. We feed it back in again until we encounter our character that indicates the stop of the tweet, the end of the tweet. So that's where we stop. And we can translate it back to the original characters. And finally, the training scripts, which is actually a lot, but let's go through it quickly. Here we define the model with slightly more units than the default. We create a session, we create a tweet sampler. We have some function to print a tweet, because we're going to print a tweet after every step of training to see how the model is improving. And the rest, I don't have time to explain, but here we're going to iterate through all the epochs and do one step of training every time. So every time it will apply this gradient descent. It will do it in batches. It will cut all this input data up into chunks and process each chunk one by one. That's pretty much what it does. So let's look at the outputs of this script. We first start by sampling a tweet without training anything, and it's gibberish. But after one epoch, we already see what thumb up. It's like Trump, probably. There's like words and stuff. It's not really English, but it's words. And then it gets better, and then it's spouting some obscenity. I didn't think he did it, you know, can't help it. This was really the outputs I got, and I needed to show it. So, but if you train it a bit more, and we get like at epoch 81, this actually starts to look like proper English. It starts doing mentions and even creates URLs down here, and you know, it's pretty convincing to me. I mean, it's not good enough to put on Twitter. Maybe it is, but you know, it's not automatic trend, but it's pretty good. So yeah, this is, I was pretty happy with the result. I picked one myself, which I thought was quite convincing. So this was it. We successfully created a Trump generator. All the code for this is on GitHub, so are the slides, because I actually implemented gradient descent in my slides to create the diagram I just showed you that does gradient descent. So it might be interesting for you. Any questions? You have 45 seconds. Yes? You don't. That's the trick with deep learning. You don't, but that's actually a really hard topic. But there are heuristics that make sure that you get pretty close. Anyone else? Yeah?
Why do you predict the next character, not the next word?
Because for modeling words properly, you need a way bigger corpus to start with, and you need word embeddings, which is a pretty complicated topic. So it's just not as simple as using word. There are like many different words, and we only have like 80 characters in this model. So it's just way more complicated to do that. But it's definitely possible, and people are actually getting way better results than this kind of stuff by using word level modeling, but it's much higher level. Okay, I think no more questions. Thank you very much. Oh. Nou, daar is wel iemand van de techniek. Hey.
Dit was dus een vrolijk verhaal.
Bedankt.